Okay, let's say we are at a playground and there is a swing. So this is that triangular support for the swing, and let's see, what does the swing look like then? There is this chain coming down, metal chain coming down from the top, and maybe a piece of let's say a piece of wooden or plastic board at the bottom, and a child could sit on this this wooden board, for example, and he or she would hold on to the chain, and then would either by swinging the legs or someone from the back pushing, start swinging. Right, that's a swing. Now I'm going to look at an example where this little child's parent is standing at the back down here behind, and helping this child along by giving a push each time the swing comes back. So there is this swinging action here. Alright, so the child swings there and swings back, and whenever it swings back, the parent gives the swing a push to help it forward. So that's our swing, and that's what you'll see in playgrounds with swings and children. Okay. Now, I am going to talk about the idea of resonance. Now, resonance is about there are a number of ideas involved in resonance. There is oscillation. Things moving to and fro, and there is the idea of an external force. Okay, there's the idea of force from outside, and there is the idea of frequencies and amplitudes, right? So all these are part of this. And in this example, let's see how the main features we can actually extract from this example that can tell us something about resonance. Well, starting from the swing, let me first talk about the idea of natural frequency. Now suppose that the parent give the child a push, just one push, and then they stand back. Okay, then the swing would just swing a bit for maybe a few times and stop. Right, assuming that the child doesn't shake the legs and try to move the swing again. So if the child just sits still, they will swing maybe a few times, and they will swing less and less, and then the swing will stop because of the friction or resistance. Now this swinging on its own has a certain frequency. We kind of roughly know how to calculate that, because this is just a pendulum, and we've seen the formula for the period of a pendulum. So we can actually estimate that if we know the length of this swing. Okay, but what I want to emphasize at this point is the idea of a natural frequency. Natural frequency is the frequency of the swing itself, or of the pendulum, or of an oscillating spring, when left on its own, all right, when it oscillates on its own without any external force. Of course, there must be this initial force that gives it a push for a very short time. Now, assuming that the force stops after that and the swing is on its own, then the frequency that it swings at on its own is called the natural frequency. So, in other words, natural frequency is the frequency when there is no external force. The frequency when it oscillates, when the system oscillates on its own. It can be this swing, or it can be a pendulum, a spring, or any other thing that oscillates. So that's the natural frequency. Now I'm going to give this a symbol which I shall use later on. I'll call this F0. It's the natural frequency. Now, natural frequency is in contrast with is like opposite to what we would have if the parent keep pushing the child. Then if the parent keep pushing regularly, all right, at regular intervals, then the parent's push would force the swing to move at a frequency that is the same as how many times the parent pushes every second. Okay, so the external force can have its own frequency, right? The external force can exert its own frequency and the parent can force the swing to move back and forth at a frequency that the parent likes. So that is the frequency from the external force. Okay, so we instead of the natural frequency, we can also have, I'll call this F. We can also have the frequency from the external force. So that's frequency. Okay, so we have these two possible frequencies. Now comes the idea of resonance. Now, if you look at, if you have actually tried pushing a swing, okay, or you've watched people pushing a child on the swing, you might have noticed that the person pushing does not just hold on to the swing and keep moving it back and forth. Right, that would be really tiring, and the swing would not swing very much. Now, what you would probably see or do if you try pushing this is to give a push to the swing, wait for the swing to swing out and come back. All right, then when the swing is on its way out again, give it another push. Give the swing another push when the swing is on its way back out. So then the swing might swing outward a bit higher, and then it swings back. And then when it's on its way out again, give it another push, and the swing would go forward again. And if you find that if you keep doing this, if you keep pushing it only when the swing starts going outwards, all right, you would help the swing to swing a bit more each time, and then you'll find that with the least amount of effort, you can make the swing go quite high up. So that's how we would do it, right? For example, when the swing is on its way back, we would not try and push it when it's on its way back, because obviously that would just slow down the swing. Okay, so you always want to push it when it's on its way out. You want to be together All right, you want to be together with the motion of the string. But if you do that, all right, if you do that, you are actually pushing at the natural frequency of the swing, because you simply wait for the swing to come back and start going forward again, and then you give it a push. All right, so you're actually following the natural frequency of the string, and you will find that when you do that, when you apply a force at the same frequency as the natural frequency of the string, the string can swing highest. It can have the biggest amplitude. Whereas if you imagine trying to push it at a different frequency, you would just get in the way, because sometimes you would try to push it forward when the swing is on its way back. You would be pushing it at the wrong times quite often. Okay, so that is not very helpful. All right, so clearly if you push the swing at a different frequency from the natural frequency, it is not effective, and the amplitude would not be as big as you might want it to be. Okay, so let me call this amplitude A. Let's say A is the amplitude of the swing, and I'm going to try and plot a graph. I'll try and plot a graph. Let's see what kind of a graph do I want. I want a graph of the amplitude of the swing against the frequency from the external force, not the natural frequency, but frequency from the external force. And let's say somewhere on the graph, maybe here, is the value of the natural frequency. It goes back and forth in this case. So let me try and imagine a number. If you've ever seen a swing or sat in a swing, you know that one swing takes maybe about like that, it goes like that, maybe a few seconds. Okay, let's say I get half a swing per second, so maybe this is 0.5 hertz. So I'm just going to put in a number, right, just for this example. So this means that maybe there will be one swing every 2 seconds. Okay, so if I push the swing at the same frequency, that means once every 2 seconds, when the swing is on its way out, I give it a push, I can get the biggest amplitude. So if I now plot the graph, right, let's say I have a ruler there to actually, or I have another friend there that actually takes ruler and measure the amplitude, I would find a certain value. Maybe there, biggest amplitude that I can get. But if I now try to push it at a different frequency, maybe more slowly or more quickly, I'll find that that for sure, all right, at some of the pushes, I will be pushing the wrong way, right? Because if I push it at a different frequency, it just does not synchronize with the swinging, right? The timing are just going to go out every now and then. So the effect is that it will actually disturb the motion. It will actually reduce the motion, and I would expect that whether you push it at a lower frequency or at a higher frequency, the amplitude is going to become smaller. Okay, so now I'm trying to figure out this graph with this these reasonings. Okay, so I would expect maybe some kind of a peak if I try to sketch a graph now around the natural frequency. So let me now try to make this graph more complete. Let's say I want to imagine what happens if I go to really low frequency. And let's try to understand what really low frequency means. Okay, we know that it means that maybe I give it a push, I wait for a long time, and then I give it another push. But I'm going to look at this extreme case, all right, just to try to get get the answer quickly. When I push it with zero frequency, what would I expect? Now, what do we mean by zero frequency? If it's zero frequency, it means that you're not pushing it, doesn't it? Well, not exactly. I can be pushing it, but at zero frequency. And what that means is that I can apply a constant force. I can just hold my hand there, all right, behind the swing or the child, and exert a fixed force and hold my hand still. So my hands don't move. So that's zero frequency, but I can still have a force. But if I do that, you can imagine what happens. If I just push gently at the swing with a fixed force, and I don't move, then the swing is just going to be displaced a bit and stay at a fixed displacement. So that would be like the amplitude, except that it's not oscillating. So it's just going to be at a fixed amplitude. Okay, so zero frequency still makes sense, right? So that means that if I plot the graph, it might be, say, some value there, right? There would be some fixed amplitude at zero frequency. So that's how I can understand zero frequency. Now let's go to the other extreme. If I am pushing it at a higher and higher frequency, what happens? So it comes down, but where does it come down to? Does it come down to zero, or does it come down to some fixed value, or does it keep, or might it go up again? So to answer that question, let me try and imagine what happens when what it means when I talk about high or very, very high frequency. What does it mean when the parent pushed the swing at a very high frequency? It means that every second the parent would push it many times. Okay, so you can imagine that it might be as if the parent hold on to the chain of the swing, okay, or hold on to the child and keep shaking it. All right, every second, just shake it many times. That's what I mean by very high frequency. Now, if the parent actually does that, then the swing is not going to the swing is going to hardly swing at all. It's just going to be shaking on the spot. And the faster the parent shake it, the less it will move. The more it will look like a vibration on the spot. So therefore, we would expect that as we go to higher and higher frequency, the amplitude would get smaller and smaller. Until at extremely high frequency, it will be just like the vibration of an object. You can hardly see the amplitude anymore. So the amplitude will probably get smaller and smaller and smaller. Okay, so now we are ready to have the graph. Let me just join the points, roughly join the points. And you can see what the overall resonance curve look like.